So this is new work for me. There will be no stochastic calculus or Brownian motion or anything like that in the talk, but I think it's a very interesting approach to data analysis. So I will spend half of the talk explaining the idea behind this approach of deep learning for those who are not familiar, and then I will detail an application to high-frequency financial data, an extremely large data set that we explored, and show what we can learn from high-frequency financial data using this approach. So, but the problem that we're interested in, and many other people are interested in, is understanding how prices are formed in markets. So during the day, if you look at the stock market, there are many buyers and sellers, tens of thousands. They look at information, they send buy and sell orders, and these orders enter this electronic system of the stock exchange. They go into a venue called the order book, and it's displayed electronically. And so this order book can be thought of as a snapshot, a real-time picture of supply and demand. So in principle, in economics, you learn that if you know supply and demand, you can determine the price. In principle, it's true, but quantitatively, how exactly do you calculate the price from supply and demand? This is difficult. And if you can understand how this works, then you have a model of price formation in the market. So, so there have been many studies in this area, theoretical models, empirical models, econometric models, and so on. So the idea is that if you observe the price history, the past price behavior, and you observe all the buy and sell orders that come in maybe now, but also in the past, maybe the past is relevant, then given all this information, can you say how the price will react? If you understand that, then you have a model for price formation, and you can think of it as a map F from price history or the flow to the next price. And all the econometric models, all the microstructure models, stochastic models, machine learning models, any kind of a model which tries to predict or determine price from supply and demand can be thought of as one example of such a model. Now this function F can be very complicated. It can depend on a lot of inputs, history of those inputs, and so on. And there have been lots of models of this type in the literature trying to understand the relation between supply, demand, past prices, and the current price. So some questions which are interesting for people in this area are, well, is this map F universal, meaning it's the same mechanism which determines the price in every market for every stock, for every, every financial asset, or is it specific to each asset? Is it the different price formation mechanism for each stock, or is the stock market different for each sector, or are stocks for retail companies different in the price formation, the way they are traded, than other stocks? So, and if you look at the theory is abstract. It doesn't say here is a model for this kind of stock, here is a model for that kind of stock. It's pretty abstract. So it seems to implicitly assume universality. But on the other hand, people who use these models tend to use only the data for stock A to build a model for stock A. Then they use data for stock B to build a model for stock B. And they never would use, mix the data or use the model estimated from data from stock A to calculate something about stock B. So it seems like they don't believe it's universal. There are some empirical studies that point to universality, but nothing really which says, okay, you can use this data for that purpose. It's still a bit, it seems that people don't believe that. And then there is the other question is this function F constant in time, or is it varying? If you estimate the function F, if you can pinpoint it using data from last month, can you use the same function F for next month, or for next year, or for 10 years ago, or okay. And again, people don't seem to believe that. There is this strong belief that financial data are somewhat non-stationary, And this is very often cited as a reason for using only recent data. So if you want to build a statistical model for stock market or interest rates or whatever, they say well, only use 1 year of data or 2 years. Even if you have 50 years of data, don't use it because it's non-stationary. Now, on the other hand, we have lots and lots of data now. So if you look, for example, at stock markets have become electronic. And every single buy or sell order or cancellation of these orders, execution of these orders is recorded in databases. And these, in large stock market, these transactions and these orders occur every millisecond or even every microsecond if you look at large, liquidly traded stocks. So if you have every microsecond a new event, yeah, that means you have petabytes of data for a year of the stock market, and this is the case. So you have, in fact, this unprecedented, you have a real-time picture of how supply and demand evolves in this market. And this is the only case I know where you have a market where you can see every millisecond or microsecond how the supply and demand evolves. So in principle, with all this data, you should be able to really estimate this function f, which maps the supply and demand to the price, and determine once and for all what it looks like. And surprisingly, people haven't done that. So most of the 99% of the models you see in econometrics use past prices to forecast future prices or their properties. They do not use the order flow, which means the buy and sell orders which arrive, and there are millions of them, to obtain information about the future pricing, which is what economists would suggest is the right way to do. And why don't they do that? Because it's difficult. Because these are very large data sets. Even if you don't sample every microsecond, but you sample every second, well, the number of orders arriving is huge. The orders are placed at different prices, so you have high-dimensional data sets, and the relation between the supply and demand and the price is nonlinear. And so it's not clear how to formulate it. There are different ways to formulate it, so there are many parameters to be estimated. And so there are, of course, many parametric models that have been used, but there's no conclusive model which says, okay, this is a stable relation which works out of sample for the relation between supply, demand, and price. And so a lot of people in the industry use high-frequency data for forecasting purposes, but they tend to use high-frequency data for one stock to forecast something about that stock, and they only use a few days of data or maybe 1 week of data. They don't really believe that if they go beyond that, it's useful because there's this non-stationarity thing that scares them. So although there's petabytes of data, I have not seen any system where this massive data is used that actually to build a model. So they're fragmented and pieces of them are used to do different things, but they're not used in their entirety. So what kind of data do we have? Well, as I said, market participants send buyers send orders to these electronic systems. And these orders are of this type. You can place an order to buy or to sell. They call it bid or ask in this jargon. And an order means you say a quantity and you say a price. So you say, I want to buy 1,000 shares at a price not higher than $79.99. And the other guy says, I want to sell 1,100 shares at a price no less than $80. And if your price is agreed, then you trade, you're executed, and you go out. If there's no price which matches your demand, then it sits there in the order book. And what we see every millisecond is a snapshot of the order book. So every time new order arrives, the order book will change, will update, and we see all these updates. So these are recorded every microsecond or even shorter time intervals. And so we have these order books for every stock all the time. So this is why it's so large. So question is, what can we learn about price formation from this data? Okay, so as I said, the typical approach is, so we have a problem that you can formulate in an abstract way like this. Mathematicians like to take a problem and make it abstract and then find the solution and then go back to the initial problem, see if it works. So here the abstract formulation is you have a very high dimensional data set. So So you can think of it as a map from some subset of a high dimensional space to the real line. So you can think of the output as the price. And you can even limit yourself to a price grid, so then the output is on a finite set. And then you want to estimate this function, and you have lots of data. You have a very large amount of data. And the problem is that the data dimension is very large. So this map is a map in a very high dimensional space. So typically, you will have the millions in dimensions, at least tens of thousands in the dimension. So one way that is used a lot in statistical modeling is linear representation. You represent this unknown map as a linear combination of features or fixed functions, and then you try to estimate the coefficients from the data. Here, because you're in very high dimensions, that's not going to work, because unless you really know what you're looking for, you will have to have a very large basis to project on, and the size of the basis you need to get a good approximation will be exponentially large in the dimension. So that's not an approach that works in large dimensions. Oops. Okay, so here the idea in these neural networks goes back to old ideas in approximation theory, representation theory of high-dimensional functions, and in fact, you can find the old result, which can be thought as, the grandfather of all these approaches. It's the Kolmogorov representation theorem. So the Kolmogorov representation theorem, which was shown by Kolmogorov, a first version was shown by Kolmogorov in 1956. Then he gave the problem to Arnold to generalize. Arnold was his PhD student then. So he was apparently 19 years old, and he solved this, and he came back, and this was his first paper. It's a problem related to Hilbert's 13 problem. In fact, it's can you represent high-dimensional functions in terms of one-dimensional functions? So there are different ways to set the problem. So in some settings the answer is negative. Hilbert gave a counterexample, for example, for functions which are the solutions of algebraic equations. But Kolmogorov was interested in positive results, so he formulated a version which gives you a nice positive result, and then it was generalized by different people, Lorentz, Pescher, and so on. So the idea is that if you have a high-dimensional function, n-dimensional function, which maps some n-dimensional variable into a real variable, a real number, you can always express it as a finite composition, not superposition, but composition of linear functions, and so at most, and the number is at most 2n, with a single nonlinear function, capital Phi, of a scalar variable. Okay, so this is the representation. It says that to represent an n-dimensional function, you need a one-dimensional function, capital Phi. Okay, and you need n one-dimensional Lipschitz functions. Okay, and then you take the sum. So you can always decompose them in this way. So all these functions are scalar. Okay, so phi p and phi are all scalar functions, and so here the important thing is that it's a composition. You compose these functions. Each of the internal functions acts on one of the variables. You pre-process each of the variables in some way, but only one-dimensional calculations. Then you take a sum, and then you do an operation on the sum, and then you take again a sum. Okay, so this is a representation of high-dimensional functions as iterated compositions of one-dimensional functions. Okay, so now this is an exact representation. But in this representation, the function capital Phi can be very irregular and badly behaved. So it's not a useful representation for building approximations. It practice, but you can use these ideas, and they have been used to build the computable approximations by, again, iterated composition of scalar functions. So the idea is that replace linear combinations by iterated compositions of scalar functions. Why is scalar important? Because scalar means you can compute them very quickly. So here I'm going to explain a little bit how this works and how it's used. So you take a fixed function, which has to be nonlinear. It's a monotone increasing function, which goes from 0 to 1. For example, in all the examples, I will use the function 1 over 1 plus exponential minus x. But you can use anything. It doesn't matter. It doesn't matter. And then you look at all the functions that you can generate by composing this activation function phi with affine functions and then doing linear combinations. So you take your vector argument x, you do linear combinations, eventually you add a constant, and then you do linear combinations after applying phi. So linear combination, phi, linear combination. That's all you do. The only nonlinear thing is phi. But the nonlinear operation is one-dimensional, so easy. Okay, so now you look at this set. Let's call it L phi. The only thing you need is a bunch of coefficients and your function phi. And then the idea is that you're going to use iterations of these functions to approximate an arbitrary function. Okay? And so this, I mean, a special case of this is the Kolmogorov representation theorem. But the Kolmogorov representation theorem, it doesn't allow you to fix the function phi. There exists functions phi 1, phi 2, phi p, but they are not nice. So here we're inspired by that. And we're going to fix the function phi, and then we're going to vary the weights. And the idea is that if you take a function of this type, which does linear combination, phi, and then linear combination, you can think of it as a neuron. So this is an analogy with biology. So this was a point of view that emerged in the 80s. So in the 1980s, there are people trying to, look at brain function, building mathematical models of brain function, and you can, break down the building block of a brain to neurons. And what's a neuron? Well, a neuron has synapses, so there are things that link it to other neurons. So these synapses take inputs. These are electrical signals coming from other neurons. And one schematic way of seeing a neuron is that the neuron takes these inputs, does a linear combination of the inputs, because the electric currents, are collected into a single channel. So there's a natural summation. And then, so this is the sigma there. It's a summation. And then if the total signal flowing into the neuron is strong enough, it activates the neuron. And activation means it triggers an output signal to other neurons. Okay, so the activation function here is a function that increases from 0 to 1. If the signal is weak, it outputs 0. If the signal is strong, it outputs 1. That's the idea. That's why it increases from 0 to 1. So it outputs something that's the phi applied to this sum. That's exactly what we do here. Okay, and if you want, you can have a bias. You can have an affine term. You have a constant. This means there is always a current coming in, and so on. So you can think of each of these elementary functions as a neuron, and then if you do so, then iteration of these means you take these neurons and connect them together. The output of a neuron goes into the next neuron, and so on. So that becomes then a neural network, as I will show you. So why do we care about this? Because actually, there's a result called the Universal Approximation theorem. So various versions of this have been shown in the literature. I'm not sure exactly who did it first and so on, but there are various versions of this: Hecht-Nielsen, Horny, Kurkova, etc., etc. All the versions have slightly different assumptions, but basically they tell you that by composing these elementary neurons, you can build approximations for arbitrary continuous functions in arbitrary dimensions. And all these building blocks are one-dimensional scalar functions. So, for example, this is one type of result. This is the one in Kurkova 92. It says that you take a function in dimension n on a bounded set, And then you take an activation function phi, which you can always think of it as 1 over 1 plus exponential minus x. It doesn't matter. Just the increasing function from 0 to 1. And then there exists, so the set L phi, remember, is the set of functions of this type with this function activation function inside. So in this set L phi, the choice is determined by the weights. So the only thing you need to choose for a function like this is what are the weights wi and ai. Okay, so you choose a bunch of weights, and it says that there exists some k such that you can approximate the function f by a sum of composition of this type. So it's a sum of functions of neuron type applied to a sum of other functions of neuron type. So you take the inputs, you apply a neuron to it, you take the output, you take the sum, you send it into another neuron, and this gives you phi, and then you do this with k different neurons. So now you can think of this type of approximation. This is a little bit more complicated. You can think of this as a 2-layer neural network. The first layer takes the inputs, runs them through a neuron. Each input runs to a neuron. So it's phi 1i is the neuron that takes in input xi. And then all of these go to another neuron. It sums them, and it applies another transformation. This is the neuron in the second layer, and you have k of these neurons. So you can think of this as a 2-layer network with n input neurons and k hidden neurons. So you can draw a picture like this. This is a diagram showing how I built the previous approximation. You take the data, you send them to some neurons. So these neurons do this linear combination, phi, a linear combination. They send it out. And then all these outputs of the first layer are inputs of the second layer, but with different weights. They do linear combinations, phi linear combination. The only thing that changes in these arrows is the weights. Each arrow carries a vector of weights, and they're different. And then you sum the outputs of the second layer. This gives you the output. And it says that the output there is a way to choose the weights in each neuron such that the output is an epsilon approximation of your favorite function f. That's the result. Okay, so here you need two layers. Okay, and there are lots of other results of this type in the literature. So more generally, you can use networks with many layers, not just 2. And usually, if it's more than 3, they call it deep, because then deep means you really it becomes non-explicit. You do iterations of these things, and then at some point you don't know what it's doing really. But what people observe is that when you increase the number of layers, you greatly increase the flexibility of the model. Then you have much more powerful approximations than just with 1 or 2 layers. Okay. So these deep neural networks have been extremely successful in pattern recognition in high dimensions, image recognition, video recognition, and so on. And what they do is really this. They take this activation function phi, and they do successively linear combination with some vector of weights, phi, linear combination, vector of weights, etc. But they do it k times, where k is the number of layers. And in each layer, you can have m neurons. Okay, so you get a diagram like this, and the resulting approximation is you can compute it by iterating through these neurons. It's very easy to program, very easy to program, because in each neuron you do linear combination and some one-dimensional function. Trivial to compute, not trivial to estimate, as we will see. So what are the parameters here? Well, the parameters at each layer, you have these weights. So theta k is the notation for the vector of weights. Okay, so you have one weight per arrow. Okay, so and if you have k layers and m neurons per layer, you have k times m squared weights. So if you have 100, 100, then you get if you have like 100 neurons per layer and 10 layers, which is not very big, you get 10 to the 5 weights. So it's not, you have large number of parameters even for fairly small architectures. So it's nothing comparable to a brain. Of course, in a brain you have billions of neurons, but even with 100 times 100, you get something like 100,000 weights. So you have to estimate these coefficients. And the way it's done, so one way to do it is supervised learning. So it means that you take this architecture with these weights, and you minimize in sample, over your data sample, some objective function, which can be a negative relative entropy of the forecasted distribution, the output distribution compared to the in-sample distribution, or some other objective function that corresponds to your application. And this optimization is an optimization over a high number of weights in a very large space. And that's what's called supervised learning. Okay? And again, because the map f theta is explicitly expressed to a recurrence relation, you can compute the gradient of f theta with respect to theta in closed form in an iterative way. So you can do a gradient-based descent to compute these loss functions and minimize them. That is what's used. Okay, so we're going to use an approach like this. Why we're going to use it? Because in the literature, people have shown that it's very efficient for representing, for non-parametric pattern recognition, for representing in a non-parametric way the relation between some high-dimensional input and a low-dimensional output, but where the relation is nonlinear and you really know nothing about it. Okay, so we're going to assume we know nothing about it, which is approximately true, and then try to learn from the data. But you need a lot of data, because if you have 100,000 parameters, well, you need much, much more data. Otherwise, no chance you're going to learn, and you're going to overfit. So that's why this application was interesting for us, because we have 3 years of high-frequency snapshots of the limit order book that I showed you earlier. So snapshots of the supply and demand curves for 1,000 stocks traded on the NASDAQ. And we have all the events that occur on the NASDAQ for these stocks. So that's hundreds of billions of order book events in this data set. So I think it's the largest data set I've ever seen in financial research studies. So we separate this data set into 2 parts. The first 2 years are used as training, so to estimate. And then we use the last year to test whether there is any stability out of sample. Otherwise, it's totally useless, of course. Not totally useless, but somewhat useless. So now you can do many things here. You can try to build models for forecasting the price, forecasting the reaction of the supply and demand to a new order. So here I'm going to show something that is simple to explain on pictures, which is here we try to predict the movement of the price given the supply and demand before time t. So up to time tau. So here let's call tau 1, tau 2 the times at which the price moves. So not all. There are events which don't move the price. A new order arrives, it sits there. It doesn't necessarily move the price. The price only moves if there are transactions, and the transactions deplete the existing orders at the best price, so and you move to the next price. So these subsamples are a thing to a size that is easier to manage. And so we say, okay, I've observed all the order book history, all the orders up to time tau k. Can I predict the direction in which the price is going to move? Is going to increase or decrease? And this is something of interest, obviously, to people in the market, because if you predict a higher than 50% probability that the price is going to go up, then you can do something with that. Okay, so so just as a benchmark, we use a linear model. So linear models are used a lot in intraday data analysis. So linear model means, well, I'm going to learn a model in which I forecast the price based on linear combinations of all the data I have. And then we're going to compare it with a multilinear deep neural network where I have this non-parametric flexible representation, which in principle allows me to capture nonlinear relations of our arbitrary type. Okay, so here we're not trying to forecast the price in dollars, but we're just trying to forecast if it goes up or down by 0, 1, 2 minus 1 minus 2 cents or less. So it's like a classification problem. We're going to classify it in 4 states, not all the possible prices. Okay. So to forecast that, there are at least 2 different ways to do it. One is to forecast based on the current state of the order book. So you only have the snapshot right now. And then a more ambitious thing is to forecast it based on the current state and all the previous states, because in fact people do think that it's relevant to look at how the order flow has been behaving over the whole day, not just right now. So we will compare both to see if the history is relevant or if it's a Markovian model where you can just look at the current state. So to do that, we use the following specification. So we're going to estimate the neural network, which takes as input. So the inputs of the neural network are the current state of the order book. So this is the picture I showed you earlier with the orders and the prices and quantities. And then there is what we call the features learned from the past. And the features HT are learned iteratively from the past. Okay. So we iterate these. So we are simultaneously estimating 2 neural networks, one which learns the relevant features from the past, and the other one which takes these features and uses them to forecast the next step. And this, I mean, you don't necessarily need to do this. You could just stack as input all the past, but that would be a hugely dimensional thing, which you don't want to do because then you have to use bigger memory and so on. And we'll see that already this is quite tough. So this is an architecture, this is a more complicated architecture than the one I showed you before. This is called a recurrent neural network, or more precisely, a recurrent long short-term memory network. And this was introduced specifically for modeling time series. Okay, so the architecture I showed you in the beginning tries to estimate a static map, but there's no time. Here we have time series, so the observations are ordered in time. So you cannot use the future to forecast the past. So you have to make sure that when you train your neural network, it only uses slices that are in the past. So you do this recursively through this double architecture. So you have 2 layers. First, you go from observations to the features, and then you go from the feature to the forecast. And the architecture is like this. So it's not directly going from X to Y, but then in this way, but you respect the order in time. Okay, so that's a detail, but it's a very important detail. Okay. So, but the way that we train it is that so at each point in time, you train this network which forecasts the feature of the next price from the features. And then when you go to the next time step, you retrain the features itself, and then you go. So it's a 2-step training. So it means that when you minimize your loss function on the data set, the loss function has two recurrences embedded in it, these 2. So you have to compute the gradient of your loss function, you have to compute the gradient of something that is the composition of f theta with h, which is itself a composition of these neurons for n other layers. But again, okay, this is not new. This is something that people have been doing in the past. So, so as I said, the method that we use is supervised learning. So at each point in time, the network with its weights gives you a forecast for the next time step. The forecast is up, down, up by more than 2, down by more than 2. And then you have the next price move which occurs. So then you compare the 2 and you look at the discrepancy between the 2, and you compute the relative entropy of the true distribution with respect to the forecasted distribution, and you choose the weights to minimize this in-sample relative entropy. That's what we do. So the number of weights is huge here, hundreds of thousands of parameters, because we use 50 neurons per layer, and we have 100 layers. And to optimize this, the standard technique is to use the stochastic gradient descent with respect to the weights. So you need to compute the gradient. Again, you have explicit way of doing it. The gradient is explicit, but it's a very high dimensional vector. You really don't want to store that vector in an array because the array will blow up your memory. So the way you do it is that you do an asynchronous stochastic gradient descent. It means that you randomly select a set of the vector, subcomponents of the vector, and you update those. And then the next step, you select another subset, you update that, and you do a gradient descent in the direction of the updated vector. So you never compute the gradient in its entirety at any point in time. You just do subsets. Okay. So again, this is what everybody is doing. It's really not our contribution. And because it's an extremely large data set, each gradient calculation requires you to go through all the data. And all the data means by terabytes at least. So it's a very highly expensive computation. So we use a cluster of 500 GPUs. And each GPU, if you know what a GPU is, it's a graphical processing unit. It's the kind of thing you have in PlayStation. And they allow a very fast computation in parallel. Okay, so this is how it works. Now I'm going to show you the results. So what we do is that we have these networks, these network models for learning about the relation between supply and demand and price. And we do two different things. We train these models, we train this model on each stock. So we use IBM stock data to learn about the relation between IBM supply and demand and IBM price. We use Microsoft data to learn about the relation from Microsoft stock. So that's what I call stock-specific models. And then we do something which is relatively strange, which is we pool them all together and say, well, if people really think there's a universal model, then it means I can take all this data, pull it together, and we train a neural network on the whole thing. And we will train it on subsets, 500 first stocks, 500 next ones, and so on, but we pull them together. And we're going to compare the single stock models with this pooled model, which we call the universal model. And if the universal model can do as good as the single stock models, then that's interesting. And in fact, what we will see is that the universal model outperforms the forecasting accuracy of stock-specific models, even if you do the training and testing on the same stock. The universal model still outperforms the stock-specific model. So that's the main outcome of this experiment. So first, okay, this is not very interesting graph. It shows that the model that you obtain by training this neural network, because it can capture nonlinear effects, beats a linear model. Okay, this is not very surprising, but it shows something, because a linear model, what can it do? If you do a linear model, it can capture trends. So if the stocks are going up, it forecasts that it's going to go up. So it can capture short-term trends. So if you compare, so here the evaluation metric that I'm going to show in all the graphs is out of sample forecast accuracy. It means I train in the first 2 years, then I take a period which is outside the training data set, and then in that period I take the actual order flow, apply the network, the function that the network has learned, and look at the forecasted price, and then I look at the percentage of observations out of sample. Well, the model predicts correctly the price move. Okay, so this gives you a number between 0 and 1. Hopefully it's larger than 50%. It is. So even for the linear model, it's larger than 50% because the linear model learns the trends. There are a lot of intraday trends. So you have an accuracy of 60% for the linear model. That's the blue histogram. But for the neural network, it's a red histogram. You go up to 70%. So you jump 10% in accuracy by accounting for nonlinear effects. So that shows that, okay, it's capturing something interesting, at least. Because on average, you increase something like 5% at least the accuracy of the model. Okay. But more interesting is this one. So now, for each stock, we train the model on the data for that specific stock. And then we train the model on all stocks. And then we compare the forecasting accuracy of the two models for that stock. And what we show here is that for most of the stocks, except perhaps 3 or 4, so here we have 489 stocks in this sample, for all of them except 3 or 4, the universal model is better in forecasting for that stock than the model trained on the own stocks data. And this is really interesting because, of course, if you pull them together, you have much more data. You have 500 times more data. So if it's 2 years for one stock, you have the equivalent of 1,000 years of history for training the universal model. And it shows that it's better. There is information in stock B's history that can be used to improve the forecast of stock A. Even information from 2 years ago in stock B can be useful for forecasting stock A today. And that's something that is captured by the model. And in fact, if you look at where the accuracy lies, well, it's just a question of data size. You see that the increase in accuracy is higher for stocks where their own data set is smaller. So if you have a stock with a short lifetime, it has been issued last year, you don't have much data. But you have lots of other stocks with a longer lifetime. But what it's saying is that they all work in the same way. All these markets function in the same way. So you can learn how this relation is from other stocks which have more data, and then you apply the model you've learned to this one, and it works. And it works. You actually get a large improvement for the stocks where you have less data. So just because pooling them together gives you a larger, more diverse set of scenarios. But of course, if the mechanisms underlying them are not the same, they're irrelevant scenarios. But this shows that they're not irrelevant scenarios because they are basically doing the same thing. Now, even but more interesting is that if you now apply the model trained on, say, 500 stocks to the other 500 stocks which you have not trained it on, because we have 1,000 stocks, it also works. So that's this graph here. So you train the model on the first 500 stocks, and then you test it on the other 500 stocks at a different period. Okay? So you train it on from in 2014 to 2015 on the first 500 stocks. You test it after the training period for other stocks. So it's out of sample in terms of time and in terms of stocks. You get the same accuracy. Orders of magnitude are exactly the same as for the ones that you are training on. So this means that the model generalizes to stocks it was not trained. It finds relevant information which is stable, not just out of sample in time, but for other stocks, and this is really the evidence that there is universality. It really works. We're not people who are doing abstract models. We're not wasting their time completely. It works similarly across stocks, and this is not totally surprising because the algorithms that are used are the same exactly in all these markets, but you know. Okay, let me skip because I don't have much time. So now, so why does it work? Well, because when you pull them together, you access a much more diverse set of scenarios. For example, you might have one stock for which during the training sample nothing is going on. It's very flat. And then you have other stocks in the training sample where you have flash crashes, they go up and down, the market crashes and so on. So now if you in the out of sample testing period, you test on a stock which has a crash, but previously did not have a crash, a model trained on the sample where there's no crash has no way of detecting this pattern which leads to a crash. It cannot learn it it's never seen it. Whereas if you have it in other stocks, it's going to learn this and learn episodes which cannot be predicted from data that you have only on the stock you're testing on. Okay, so this nobody really does it like this. Nobody pools this data from different stocks for estimating a model because they think that they're different. This is different: agriculture, retail, electronics, and so on. But at high frequency, why is it different? The same algorithms are trading them. This analysis is suggesting that the benefits from pooling the stocks and this argument of universality outweighs any argument for heterogeneity and not pooling them. Now, stationarity across time. As I said, another very strong idea here is that it's non-stationary. You shouldn't use data unless it's recent data because the market changes, things change, and we don't know what's. Well, here what we did is we trained it on the period of up to May 2015, and then here, and we tested it out of sample for the next periods. But so if this stationarity, if this non-stationarity thing is correct, then the farther you go from the test, the farther are the test period and the training period, the worse should be the accuracy. Because if things change and it's not stationary, well, if you test 1 day ahead, 1 month ahead, 3 months ahead, 6 months ahead, you should be worse and worse. Well, this what you see in these graphs is the histogram of the accuracy score across stock. So each point in the histogram is one stock for a test period starting in June 2015. So right after the training period. So that's the left, and the right is a test period in January to March 2017. So nearly 2 years later. Now, there is no real difference between the two graphs. There's no real gain in accuracy if you do it right after your training period than if you do it 1.5 years later. So this is really an example where you see that it's pretty stable across time. It's pretty stable across time. The performance is same 1 month later, 2 months later, 1.5 years later. And this was really surprising for me. I did not expect that. In fact, but if you think about it, we are not estimating the volatility of the stock. We're not estimating this kind of thing. We are estimating the relation between the order flow and the price. This relation is stable, is the same there and here. What is not stable is the characteristics of this order flow. The order flow may be more volatile here and there. Therefore, the stock is more volatile, but this is okay. The map doesn't need to change. And what you see is that the map doesn't really change. And this has implications because people really are very resistant to using a non-recent data. They say, it changes all the time. You should use short windows and so on. Here, we don't find any evidence that it's better to use a shorter window. In fact, here what we do is that we use training sets that are more recent, less recent, and so on. So the training set goes back 1 month, 3 months, and 6 months, and so on. So what we show in this table is that it is not true that if you use a more recent period, you have a higher accuracy. It is not true. What is relevant is the size of the data set. What is not relevant is how recent it is. It's not true that if you move the window closer, you increase your training accuracy. In fact, with these models, the main danger is overfitting. And if you less data, you're going to overfit. So you will deteriorate out-of-sample performance, whereas large data sets will improve the estimation. Now, the last thing that I want to show is history dependence or path dependence. So of course, this approach to using order flow to forecast the price, there's also stochastic models, analytical models that have been proposed and used. But these analytical models are mostly Markovian models because otherwise it becomes intractable. So the question is it Markovian? So you can do a non-parametric test here. You train 2 neural networks, one which takes as input only the current state of the order book, and one which takes as input the history of the order book, 100 steps back, 500 steps back, 2,000 steps back, and so on. And you look if you improve, if you take the history. For a Markov process, you should not improve. Well, here you do improve. So this is the increase in accuracy, 1 point for each stock in the histogram, comparing the long short-term memory network with memory, with a feed-forward neural network with only the current state as input. Okay? So you see that you improve the accuracy roughly, 4 to 10% depending on the stock, but that's a lot because we're, the improving accuracy by 5% is a lot. It's of the same order as the difference between linear and nonlinear model. So yes, history is relevant. And in fact, you see that if you go from 100 lags to 5,000 lags, so what are lags here? Remember, I sample every price change. So on average for these stocks, price changes every second or so, 1.7 seconds on average. So 5,000 events is something like 2 hours. So it means that if you want to forecast for the next fraction of a second, if you go back 2 hours, it improves your forecast. The information 2 hours ago is relevant to forecasting the next fraction of a second. It's compared to 100 events, which is around 2 minutes. So it's not because you do high frequency forecasting that you only need to look at 1 minute. You need to look at longer. And of course, it's not so simple. It's very difficult to build path-dependent, history-dependent models which have some analytical tractability. But I think one of the strongest arguments for this approach to modeling is that it handles history dependence well with this LSTM architecture. So you can have non-Markovian systems and you can still train it and get interesting information. Okay, so let me summarize. So we've shown how a deep learning approach works and how applying to it high frequency financial database uncovers evidence of a universal price formation model that relates the order flow to the price. So here, but universal means that it's stable across stocks and sectors, and it's insensitive to the details of what the stock is. And what we show is that the universal model trained on the pooled data, much larger data set, outperforms in terms of forecasting accuracy stock-specific models trained on the stock you would like to forecast. So this leads to the counterintuitive thing that you should use data from other stocks if you want to forecast, even if you want to forecast only this stock, not just the thing you want to forecast. And this is not something people have been doing. We also show that the relation uncovered by the deep network is stable across time, even like a year out of the sample, without any adjustment to the model. We're not renormalizing the series by volatility adjustment or something. No adjustment, exactly the same coefficients in the network. We apply them 1 year out of the sample. And if we look at the features of the map that we estimate from the data, it shows strong path dependence. It is relevant to look at the history. It is not a Markovian system where you can forecast things from a snapshot of the current state. You need to look at the history of the state of the order book.